When the sun is shining at a bright day, everything seems so colorful. Several people like to sunbath, protecting them against the ultraviolet radiation from the sun. Apparently, things around us and ourselves are sensitive to sunlight. Despite the sunlight looks white to yellowish, it consists of many different colors, which we can clearly see once rain droplets diffract these lights, creating a rainbow. Wouldn't it be great if we can use this kind of colors to analyze the interaction with matter? So let's do that and see how this sunlight falls with the electromagnetic spectrum. The ultraviolet and visible light parts of the electromagnetic spectrum is small if we look at the various frequencies or wavelengths there are in this spectrum. Each part of this electromagnetic spectrum interacts differently with matter, and so does ultraviolet light and visible light, but also infrared light. Nevertheless, what the radiation is, matter reflects, absorbs, and transmits it to a certain extent. And since radiation is a form of energy, it cannot be lost, and so the total energy of the reflected, absorbed and transmitted light is equal to the energy of the radiation that was used to irradiate that matter. Since matter basically consists of electrons, protons and neutrons, these species individually or together must be responsible for the change of this radiation. The part that is penetrating matter is the difference between the incoming radiations and the reflected part. From there it is possible to calculate the absorption by measuring the transmitted part, taking the reflected part into account. The absorption occurs by bringing electrons in a higher energy level, a so-called excited state. This transition from electrons to an excited state can be a fingerprint of the material and thus is a material's property. Normalizing the measured absorption by the sample thickness d with the so-called Lambert-Beer law, it is possible to calculate the absorption coefficient, alpha. This equation can also be used for fluids with dissolved salts. There it must be normalized by its concentration. Unfortunately, most electrode materials absorb many wavelengths of the UV spectrum and therefore are hard to use as elemental analysis. Nevertheless, it may be of importance in analyzing the compositions of components during the synthesis process in solution or jelly phase, but also in a hydrothermal recycling process where typically the metal ions are in an aqueous solution. These dissolved ions all have their specific color depending on the environment. In other words, it depends on the kind of salt that has been dissolved. For instance, cobalt-free plus ion salts give us a nice color palette, showing almost all colors from the rainbow. This palette is also known as a spectrochemical series. The color is an indication of which part of the ultraviolet visible spectrum is absorbed. This is typically measured by UV-Vis spectrometers. By adequate calibration, also the concentration can be calculated. Even by eye it is possible to have an indication of the absorption of the various solutions, which can be made clear by the so-called color wheel. In this color wheel, the primary colors, blue, red and yellow, are mixed to form the secondary colors, and on their turn mixed again to form the tertiary colors. The wavelengths run from say 350 violet to 700 nanometer, which is red. It turns out that matter that transmits or reflects a blue color absorbs orange, the exact opposite color in the color wheel. Similarly, matter that is yellow absorbs purple violet light. Not only the environment of the ion is responsible for the color, also the oxidation state of the transition metal ion. That is why we see so many colors from the transition metal ions, caused by their environment but also by their oxidation state. Here too we could analyze the absorption by using the color wheel. However, the situation becomes a little difficult once we have mixtures of absorbing salts, or once a salt absorbs more wavelengths. Then we really need to measure the spectrum with a UV-Vis spectrometer. This situation occurs, for instance, for vanadium ions. The use of spectrometers is also interesting during charging and discharging a battery, because the oxidation state changes of the transition metal ion. Despite the method, it is less suitable for analyzing solid electrode materials which are in a closed container. Nevertheless, in redox flow batteries, the colors of the various metal ions are nice to obtain in, for instance, vanadium redox flow batteries. Here the vanadium 2 plus is purple, vanadium 3 plus green, vanadium 4 plus blue and vanadium 5 plus yellow. These vanadium ions have various wavelengths which are being absorbed. That means to figure out the color, we see it's difficult to conclude the absorption wavelengths which it will be. Vice versa, once we measure the absorption, we can analyze the color of the material by subtracting these absorbed colors from the solar spectrum and see what is left. For instance, vanadium 2 plus absorbs practically all colors from the blue to red, and that means purple remains. Vanadium 3 plus absorbs the purple and blue and the yellow to red part, but not the green part, and thus it is green. The same strategy will be a blue color for vanadium 4 plus. For vanadium 5 plus, we can use the color wheel. Absorption of purple gives us a yellow color. By measuring the absorption of the vanadium 2 plus and 3 plus ions, concentration of the negative electrode tank, it is possible to calculate the state of charge. Here the purple curve represents the vanadium 2 plus and the green one the vanadium 3 plus. The blue curve is the sum of both and is falling completely over the vanadium 2 plus curve because there is hardly any vanadium 3 plus. However, at lower state of charge, the green curve becomes more and more visible because vanadium 3 plus ions are produced. This becomes even more significant at lower state of charge, at 60, 40 and 20% state of charge. UV-Vis can also be used for measuring the concentration of combinations of transition metals in recycling processes, such as the hydrometallurgical method. In this method, the end-of-life batteries, EOL, are first completely discharged to avoid accidents. Then these batteries are dismantled to recover the casing. The rest is crushed and riddled and a solvent N-pyrimidine, NMP, is being added to dissolve the binder and free the active components. After filtration, the copper and aluminum current collector materials and the separator foils can be removed, and the remaining is the so-called black mass. Treating this black mass with a strong acid, carbon can be removed and metals dissolve. These dissolved metals thus can be measured with ultraviolet visible light. Also, after the next step of adding a strong base to precipitate the precious metals and hydroxides can be used to measure the various transition metals. In summary, we can use UV-Vis spectrometry to measure colored electrode materials, calculate the state of charge in redox flow systems, and analyze dissolved salts in recycling steps.